Hello, I would like to thank the committee for the opportunity to present at OOPSLA. I will present work on graph reduction and equivalence of CFL-reachability and type-based analysis. And this paper is a tale of two program analysis techniques, CFL-reachability and a certain type-based analysis, and the connection between the two techniques. Context-free language reachability is a highly precise and widely used program analysis technique. Type-based analysis uses type qualifiers and typing rules that entail a certain reachability semantics. While not as widely used as CFL-reachability, examples of this analysis technique include RIME, a reference immutability analysis, droid-infer, a taint analysis for Android, and NRJ, an analysis that enables safe approximate computing. There are also examples from secure computation and other problem domains. In addition, the Checker framework is a powerful tool for coding type-based analysis for Java. This analysis helps programmers find null pointers, SQL injection, and other kinds of vulnerabilities. So CFL reachability typically proceeds in two phases, graph construction and reachability analysis. Consider the program fragment. Class A has a field f and a set and get methods that respectively write field f and read and return field f. We have two instantiations of A, E, and G. Next, we have two sets of calls to set and get. One set calls set and then get on receiver E, and the other calls set and then get on receiver G. Importantly, there is flow from A to B due to the call sites 1 and 2, and there is flow from C to D due to the call sites 3 and 4. The program is represented by the following graph. CFL reachability makes use of parentheses to denote calls and returns, and brackets to denote field writes and field reads. Reachability analysis decides whether there is flow from one node to another. Roughly, if the string on the path from node A to node B belongs to the language of balanced parentheses, then there is flow from A to B. Otherwise, there is not. For example, there is flow from lowercase a to lowercase b via path A, P, this, E, this get, ret, and then B. The string along this path is shown here. The parentheses on the path match. Call 1 matches with return from call site 1, and call 2 matches with return from call site 2. There is no path from E to D, however, because E flows into this of get at call site 2, and ret flows to D at return from a completely different call site 4. So type-based analysis is seemingly very different. It makes use of type qualifiers, pose, nag, and poly, and typing rules that specify the reachability semantics. Pose is the positive qualifier, nag is the negative one, and poly is the polymorphic qualifier. The programmer annotates a subset of the variables as positive sources or negative sinks. The analysis then infers types for the rest of the variables and checks the program. If the program is type correct, that means there is no flow from a positive source to a negative sink. If it is type incorrect, that means there could be flow from a source to a sink. For example, in this fragment, both A and B are positive. The fragment is type correct because a positive variable may flow to a positive one. However, in the second fragment, C is positive and D is negative. The analysis issues a type error because a positive variable cannot flow to a negative one. One may wonder of the motivation behind this work, given that both CFL reachability and type-based analysis are well-known techniques. Our original motivation was to better understand the type-based analysis, which had proven useful for taint analysis for Android. The connection of type-based analysis to CFL reachability would lead to using CFL reachability to illuminate and explain type errors. But as we delved deeper, we found that there was room for better understanding of CFL reachability in the presence of mutable heap data. With the standard approach, mutable data entails a bidirectional graph where essentially each statement triggers both a forward and an inverse edge. We came upon a graph reduction strategy, and graph reduction typically leads to precision improvement. We make the following contributions. We propose a new dynamic semantics for reasoning about flow and reachability. We propose a graph reduction technique via reasoning about reference immutability and a corresponding correctness argument. Finally, what was our original goal, we show equivalence of a CFL reachability analysis and a type-based analysis. This proves correctness of the type-based analysis and sets forth the blueprint for explaining type errors. Next, I will outline the three contributions. Details and proofs can be found in the paper. So our dynamic semantics introduces the concept of the chain, which tracks flow from one stack variable to another. For example, the following chain tracks flow from parameter p in context of invocation 1 to return variable ret in context of invocation 2. This chain is represented by an appropriately annotated path from p to ret in the CFL reachability graph. As chains account for flow from one stack variable to another, they're appropriately represented in the graph. Note that the nodes in the graph are stack variables, and the graph completely eschews heap objects and reasoning about heap objects. For the most part, reasoning about chains is straightforward. The interesting case arises when there is a chain due to a pair of a field read and a field write. So consider such a pair here. This vs.f equals p and ret equals this of g.f is such that this vs.f and this of g.f are aliases via some heap object O1. So in our semantics, this leads to a chain from P in context 1 to ret in context 2. And normally in static analysis, reasoning about such flow is done via points to relations. So tracking that this of S points to object O1 and this of G points to the same object O1. So the main idea in our work is to turn reasoning in terms of points to relations into reasoning in terms of reachability relations between stack variables. So the key intuition here is that aliasing entails chains E to this of S and E to this of G. Here, where E is the left-hand side of the creation site of object O1. So this observation allows us to make an inductive argument for the representation of the P to ret chain in the graph. So if E to this of S and E to this of G are appropriately represented in the graph, then P to ret is appropriately represented in the graph as well. Next, we discuss graph reduction. Mutable data requires a bidirectional graph. So consider the code snippet. It triggers the following forward edges. There is an edge from A to X due to the field write x.f equals A. There is an edge from Y to X due to the assignment Y equals X, and so on. In addition, we also have corresponding inverse edges, where each inverse edge reverses the direction of flow and the annotation. For example, in the inverse edge from X to A, the field write annotation becomes a field read annotation. Inverse edges are necessary because the local analysis that constructs the graph has no way of knowing where variables flow and what happens to variables in the program. For example, y may flow along some long path to some y prime, making y prime and x aliases. If there is a write into field f of y prime, then there must be a way to track the flow of D to C along the path of y prime, y, x, and c. So inverse edges enable this tracking. Here in this work we make an observation. If a reference x is immutable, then there is no need to add inverse edges from x. And returning to our original example, the code gives rise to the following graph of forward edges. The standard approach adds a corresponding inverse edge for each forward edge. Again, this is necessary because the local analysis that constructs the graph has no way of knowing where B, for example, flows to, and whether B is modified, and we'll have to track the write back to a read from A. Our approach, on the other hand, makes use of reference immutability. Reference immutability proves that all references except for this of set are immutable. Therefore, our approach avoids adding the inverse edges except for the edges that start at the mutable reference this of set to E and this of set to G. We construct the standard bidirectional graph GBI as follows. So at each statement, we add a forward edge and an inverse edge. For example, at x equals y, we add a forward edge from y to x and an inverse edge from x to y. We construct our graph GRI as follows. At each statement, we add a forward edge. If the left-hand side of the assignment is not immutable, we add an inverse edge. Therefore, we add inverse edges only if reference immutability fails to prove the target reference immutable. Our key theorem states that all chains are represented in GRI. There is evidence of the impact of graph reduction on precision. In previous work, we reported that graph reduction improves precision of taint analysis for Java web applications. So analysis over GRI finds 20 to 80% fewer variables flow to sinks compared to analysis over GBI. For this paper, we ran similar experiments for taint analysis for Android. But most interestingly, Zhang and Su propose a novel CFL reachability technique, linear conjunctive reachability. The experiments show that linear conjunctive reachability results in good precision improvement over GRI graphs, while it results in more modest improvement over GBI graphs. We are interested to better understand the impact of graph reduction via reference immutability, whether it enables advanced CFL reachability techniques. Our third contribution is the equivalence of a certain CFL reachability analysis and a certain type-based analysis. Specifically, we consider CSFI plus, which is a CFL reachability analysis over GRI. CSFI plus is a context-sensitive, partially filled-in sensitive analysis. We consider FlowCFL, which is a type-based analysis. One instance of FlowCFL is Droiding for our taint analysis for Android. FlowCFL is defined in terms of type qualifiers, typing rules, and a type inference driven by those rules. Our theorem states that CSFI plus and FlowCFL produce the same result. To motivate our interest in the connection between type-based analysis and CFL reachability, I would like to show an example from the analysis of the Zillow Android app. Our tool Droidinfer produced hundreds of type errors across a set of popular Google Play Store apps, indicating potential leaks of sensitive data, including the error shown here. But the type error itself, which shows flow from some positive variable R4 to the negative parameter float URL, is not particularly useful. So we mapped this error to a CFL reachability path, which revealed the leak of the phone number string to the network through the load URL parameter. This leak happens via a sequence of method calls, field writes, and field reads. The CFL reachability path helped explain the type error, and in fact, in this case, we were able to trigger and observe this leak dynamically. Related work includes work on CFL reachability, type-based analysis, and work on novel CFL reachability techniques. Regarding graph reduction via reference immutability, this is an old idea of ours, and we have used these ideas in an ad hoc way in previous works. In this paper, we present a formal account and an argument for the correctness of analysis over GRI. We hope that GRI can become the standard graph for CFL reachability analysis over mutable heap data. We have presented a dynamic semantics, graph reduction, and a correctness argument, as well as an argument for the equivalence of CFL reachability and type-based analysis. In future work, we'll expand our empirical investigation of the impact of graph reduction and we'll expand our analyses. Thank you.